Hello, listeners. As an enhancement to your listening experience, I am now going to present these archive episodes unedited in their entirety, which includes all of my afterthoughts. So, continue listening after the outro music if you want to hear what I thought of the episode. And if you're enjoying the podcast, please support it by going to the homepage, spacerockethistory.com, and clicking on the orange donate button or the Patreon link. And now I can also accept Zelle and Venmo. Just use my email address, spacerockethistory@gmail.com. Thanks.
We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
Godspeed, John Glenn.
Roger, 0G, and I feel fine.
I feel out. Okay, I'm out.
How does it feel for the United States to be the new record holder?
At last, huh? When that baby lights, there's no doubt about it.
Liftoff. We have a liftoff. 32 minutes past the hour. Liftoff on Apollo 11.
Listen, Tranquility Base here. The Eagle has landed.
That's one small step for man, one giant leap for mankind.
Hello and welcome. This is Michael Annis, and you're listening to episode 240 of the Space Rocket History Podcast. And now, Apollo 12, the Saturn V Instrument Unit. The Saturn V was designed to launch large payloads into space. The payloads could be automated probes or manned spacecraft. To launch unmanned probes, the Saturn V needed its own control system, and its payload would have its own separate control system as well. Initially, there was some discussion about allowing the Saturn V to be controlled from the Apollo command module for manned flights, but this idea was adamantly opposed by the group at Marshall Space Flight Center, and as a result, all Saturn V's were launched with their own independent control system. That decision saved the flight of Apollo 12 and possibly 3 astronauts' lives. The purpose of the Saturn V's control system was to stabilize flight, manage the rocket's systems, and guide the Saturn V to its destination. The Saturn V's control system was housed inside and also referred to as the Instrument Unit. Marshall Space Flight Center's Astrionics laboratory categorized the IU, or Instrument Unit, as the brain and nerve center of the Saturn V. Here is a clip from Brooks Moore, director of the Marshall Space Flight Center Astrionics lab between 1967 and 1974. I want to apologize for the poor quality of these clips.
The Saturn V is to this day the largest and most powerful rocket ever flown, but it wasn't all muscle. It also had a mighty brain that controlled every move from launch until the third stage put the Apollo spacecraft on a trajectory to the moon. That brain was the instrument unit, the IU ring. The IU is just a small segment which sits on top of the third propelled stage. So it's insignificant in size, but it is far out of proportion in importance.
The basic functions of the instrument unit included 1. Guidance and control during all phases of flight. 2. Command and sequence of the vehicle's functions, including engine cutoff and separation of stages. 3. Insertion into orbit. And 4. Relaying of data on the Saturn V's position, functions, and other information to ground stations. The IU was in control of the Saturn V from immediately before liftoff through the translunar injection burn.
Inside the IU, there were 2 computers. The launch vehicle digital computer, which performed the navigation and guidance calculations or the heavy thinking for the vehicle, That's determining where the vehicle is and with the guidance equations where you expect it to go in order to complete the mission. And the analog flight control computer, which issued the commands that made the engine swivel to control the rocket's flight path. Connecting the two was the launch vehicle data adapter. It acted as the translator that enabled analog and digital units to communicate. It also served as an interface between the LVDC and the other electronic components and the three propelled stages. The three stages sitting on the launch pad would be completely useless without the IU. It would be sitting there not knowing what to do, where it's supposed to go, or how to get there.
The IU consisted of 5 major systems. 1. Structural. 2. Guidance and control. 3. Electrical. 4. Instrumentation. And 5. Environmental control. The instrument unit's structure was a thin cylinder about 1 meter high and 7.6 meters in diameter, with equipment mounted to its interior wall. The IU was located on top of the S4B third stage. The structure was assembled by IBM Huntsville with assistance from Marshall Space Flight Center. The structure was made of a honeycombed aluminum alloy core faced by a sheet of aluminum alloy 0.51 millimeters thick on the inside and 0.76 millimeters thick on the outside. The skin of the IU was more like that of the Apollo spacecraft than the skin of the Saturn V stages. The walls were produced as 3 parts of a ring, each of 120 degrees, to form the ring. The 3 sections were held together by splicing plates on the inside and outside of the IU. The internal equipment was mounted either directly onto the inside wall of the IU, or, if equipment needed active cooling, as much of it did, it was mounted onto cold plates that were attached to the inside walls. The IU was subdivided into 24 sections in order to locate the equipment. A cable tray was placed around the top of the IU, containing a duct for environmental control system cooling and a harness for running cables to the IU components below it. There was also an entrance door for personnel to enter and work inside the IU. But the cylindrical IU structure did more than carry meters of cable, black boxes, and other miscellaneous paraphernalia. It was a load-bearing structure as well, with 3 major rocket stages stacked beneath it and thousands of pounds of spacecraft, lunar landing module, and 3 astronauts to support above it. The next major system of the instrument unit was the guidance and control system.
The purpose of a guidance system is to point those engines, which are at the bottom of the rocket, point them in the right direction so that the vehicle gradually ascends off the launch pad and then tilts in a desired trajectory to wherever it is you're trying to go. In the case of the Saturn, it would go into Earth orbit, and then once everything was checked out there, it would restart and go on its way to the moon. Basically, you get from the ground into space in about 10 minutes, or less sometimes. And there is no way that a human being can really make a lot of decisions about controlling that operation. It has to be done automatically. That all has to be done in a very careful sequence with split-second timing. You have to be sure that one thing is jettisoned before the next one is lit, and then you do it again. The third stage takes over after the second stage burns out. So you have this very complex choreography of burning, of staging, of the gimbaling, the swiveling of the engines to keep it balanced, the tilting in the right direction. All of that has to be done by the onboard computer and the guidance system, which in this case was contained in that instrument unit.
A rocket with a destination needs a guidance system to get there. Whether the rocket is a missile or a manned rocket, in spaceflight. Robert Goddard struck on the idea of using gyroscopes as early as 1907. His first gyroscopically guided rocket flew on April 19, 1932. Wernher von Braun liked the idea so much that he used gyros to guide the V-2. Once von Braun's team relocated to the United States, they worked with the military to continue to develop missile guidance systems, including systems for the Redstone, Jupiter, and the Titan II. When von Braun went to Marshall Space Flight Center, these guidance platforms were combined with the ASC-15 flight computer developed by IBM. But the Apollo needed guidance systems that could operate longer than the relatively short time required for an ICBM. This led to the development of the more capable and longer-lasting STU-124 inertial guidance platform. So, the key items for guidance and control used in the Saturn V instrument unit were 1. The ST-124 stabilized platform, 2. The launch vehicle digital computer, 3. The launch vehicle data adapter, and 4. The analog flight computer. We'll start with the ST-124. The ST-124 stabilized platform was produced for IBM by the Navigation and Control Division of the Bendix Corporation. The ST-124 consisted of a 3 degrees of freedom inertial platform gyroscope. The platform's structural members and most of its components were fabricated of beryllium, an extremely lightweight space-age metal. Although difficult to work with, beryllium offered significant weight savings and provided good stability over a wide range of temperature. There was an interesting procedure required to align the ST-124 platform just before launch. The procedure called for a precisely sighted theodolite not far from the launch pad to aim a beam of light through a small opening in the IU, high above the ground. The beam passed through a small window in the guidance platform where a pair of platform prisms reflected the beam back to the theodolite. Coded to work with 2 different wavelengths, the prisms aided in aligning the platform to its launch azimuth. When proper alignment was achieved, the acquisition light signal notified Mission Control Center. Perhaps the most innovative portion of the guidance and control system was the launch vehicle digital computer. This digital computer was built by IBM. It weighed 80 pounds. It had real random access memory and the ability to run a stored program. It was extremely reliable and used some of the earliest microchips as logic blocks. The integrated circuit logic chips were made by IBM as well, using construction similar to that of modern-day chips. The chips were mounted on a 2.5 by 3 inch board back to back. This was called a logic page assembly. There were 35 chips per printed circuit board. These early printed circuit boards with integrated circuit chips were of great historical significance, and they have been called the mother of all motherboards. The launch vehicle digital computer used an early form of computer memory called ferrite magnetic core memory. Each tiny core, or donut, stored 1 bit of digital data either as a 1 or a 0. This was achieved by magnetizing each core in one of 2 directions. The total memory capacity was 112 kilobytes. For reliability purposes, the memory was duplexed, meaning that half the modules held duplicate data. This not only reduced the chances of system failure, but operated so that one memory system could correct the other if intermittent failure should occur. To further enhance reliability, the guidance system featured the first computer application where all critical circuits in both the computer and data adapter were triplicated. Triple modular redundancy, giving nearly ultimate operative reliability. Designers selected 7 functional sections where catastrophic failure might occur, but for reasons of reliability could not be permitted to occur. Each selected section was then placed in 3 identical but independent logic channels. Problems were presented to each module simultaneously, and the result of each, independently derived, went to a majority rule voter circuit. Any dissenting vote was discarded as an error, and the only signal passed along by the voter circuit consisted of the identical signals from 2 of the modules. In addition to the digital computer, there was also an analog computer. The analog computer basically accepted commands from the digital computer to steer the Saturn. This brings us to the data adapter. The basic function of the data adapter was that of a gateway to the digital computer for all elements of the Saturn V's guidance system. It received inputs from the ground control computer, radio command channel, telemetry, various communications from within the vehicle, the inertial guidance platform, and the flight control computer. For example, analog inputs from various sensors were taken by the data adapter and digitized for the digital computer. Computer outputs were relayed back to the data adapter for conversion to analog signals as required. If the signals involved control commands, they went through the analog flight control computer and were combined with additional signals from the rate gyros. The resulting output included commands to activate the engine gimbal systems, thereby changing the direction of their thrust and the attitude of the launch vehicle. Now for some details on how the staging worked on the Saturn V. The events of a Saturn V flight were grouped into what was called time bases. The launch vehicle digital computer controlled these time bases and sequenced the events therein. There were 8 time bases as follows: Time base 1, liftoff; Time base 2, first stage cutoff; Time base 3, staging and stage 2 control; Time base 4, staging and third stage control; Time base 5, transition to orbital coast; Time base 6, third stage restart; Time base 7, begin translunar coast; and Time base 8, propulsive dump. So, from balancing the rocket on its flame at liftoff, through the roll program, the pitch program, cutoff, staging, startups, tower ejection, orbital insertion, translunar injection burn, and the final burn to put the S4B third stage into the moon or solar orbit following separation, was all orchestrated and decided upon by the launch vehicle digital computer.
It would switch from stage to stage as the vehicle traversed. During the first stage burn, the IU monitored the propellant levels in the stage's tanks. When the first stage is near burnout, a signal is given to cut those engines off, to separate the stage, and also to ignite second stage. Likewise, when the second stage is near completion, the LVDC generates those same commands, and a signal is sent to cut those engines off and to separate, and then you have the third stage. For all 3 stages, all of these steps had to happen at exactly the right moment. Not too early, not too late, for the Saturn V to make it first into Earth orbit and then onto a trajectory to the moon.
It is interesting to note that all the carefully engineered complexities of the Saturn guidance and control system were not fully utilized during the first stage burn. Although the ST-124 was supplying velocity and attitude data to the guidance computer during the first stage burn, the vehicle did not require an active guidance system during this first stage boost. In ascent through the atmosphere, the Saturn V was subject to possible sudden stresses from gust, wind shear, and jet streams. If the guidance computer acting on signals from the stabilized platform attempted to generate compensation maneuvers during such turbulence, the added stress forces from the powerful engines as they went through extensive gimbaling motions might have caused the rocket to break up. So, during the first stage, the rocket flew according to a predetermined program stored in its guidance computer. If the vehicle was forced off course, the ST-124 sensed this displacement and fed the data into the computer for later retrieval. During the second and third stage burns, the stored data was run through the computer and into the active guidance and control system to put the rocket back on course. Information on yaw, pitch, roll, and acceleration provided by the ST-124, as well as inputs from other electrical systems, were collectively assimilated and processed by the launch vehicle digital computer and the data adapter to give the rocket an optimum performance. Moving on, the telemetry system was also in the IU. It tracked the Saturn's trajectory and orbit and transmitted reams of data back to the ground. Several tracking and command systems were employed. An ASUSA system measured slant range and vehicle direction in relation to ground stations. A C-band radar transponder aided radar ground stations in measuring azimuth, elevation, and range. During the launch and orbital phases, transducers throughout the vehicle reported information on vibrations, pressures, temperatures, and various operations. The measuring and telemetry system transmitted these data to ground stations. This not only furnished real-time data on the vehicle's performance during the mission, but provided a means of checkout for succeeding events, verified commands to the vehicle, and created a bank of data for later analysis of the vehicle's overall performance. Operation of the instrument unit equipment generated considerable amounts of heat, which had to be transferred away from the components and dissipated into space. This was the function of the environmental control system. It consisted of cold plates as mounting surfaces for most of the electronic gear, and integral coolant passages for thermal control of the digital computer, the data adapter, the flight control computer, and the ST-124 platform. Heat was dissipated to a coolant mixture similar to the antifreeze used in a car. This coolant was pumped through the 16 cold plates and the integral coolant passages. Also located in the instrument unit was the emergency detection system.
The Apollo rocket was designed with an escape system in case the rocket failed at launch or during the first stage flight. The IU ring was the brains of that system. It sent an abort alert command to the command module if a malfunction was detected in the launch vehicle. The launch vehicle system has to function during those high vibration or high G periods of flight. This emergency detection system reacted to emergency situations in one of two ways, depending on the seriousness. If the EDS sensed a situation that would lead to rapid vehicle breakup, it automatically initiated an abort sequence for the safety of the Apollo crew. The command module was separated from the vehicle and abort motors were ignited to pull the astronauts to safety. But if the emergency was one where the crew had time to evaluate the situation. The ADS sent signals that lit up the capsule's control panel with red lights. Mission Control would see the same problems on their screens, and the crew or Mission Control then made the decision of whether or not to manually initiate an abort sequence.
That was always the thought, how reliable is this going to be? What's the probability that this thing is going to fail?
Fortunately, that never happened. With the IU's help, the Saturn V never failed.
If it became necessary to abort the mission, each Saturn V carried a propellant dispersion system. This system was used as a method to destroy the rocket at any stage of flight, but after the astronaut crew had separated from the rocket. The emergency detection system operated in two modes. The first mode was automatic. This lasted from liftoff until max Q. It was believed that any catastrophe during this time would happen too quickly for the crew to make an abort. So in the case of structural failure between the instrument unit and the command module, or engine failure or excessive roll, pitch, or yaw, the emergency detection system would stop the engines, release the command module, fire the escape rocket, and then blow itself up. The second mode was switched to by the crew at T+2 minutes. You may remember hearing the crew on the radio call out EDS to manual. This meant that they had switched the emergency detection system to the manual mode. Now that the flight had passed max Q, a vehicle breakup was considered unlikely to occur before the crew or Houston could make an abort call. The final major system of the instrument unit was the electrical system. The power to run this complex electronic equipment emanated from four 28-volt DC batteries, which consisted of special distributors and regulators for both low-voltage components and higher currents for the ST-124 inertial platform. Which brings us back to Apollo 12.
The Apollo 12 mission was a very interesting one. It was the second mission to the moon, and it was launched from Cape Canaveral during some cloudy weather.
3, 2, 1.
As the rocket ascended into space off the ground, it had this enormous plume of flame coming out of the engines, which created a path of electrical conductivity, like a lightning rod. The rocket, therefore, conducted electricity and received a couple of very, very big lightning jolts, which knocked out essentially all the signals on the command module. Everything either went blank or turned red. Things were just completely shut down. But the guidance system in the instrument unit was designed to be rugged enough to handle situations like that. It kept working. They made it into orbit. Once they were in orbit, they were able to reset all the circuit breakers and realign the gyros on board. They went to the moon and had one of the most successful missions of the entire Apollo program.
When the lightning struck Apollo 12 and the command module lost everything, the reliable instrument unit continued to fly the Saturn V without interruption. The instrument unit saved the Apollo 12 mission. Salutations from northern Alabama. This is Michael Annis, your host. I wanted to say thanks for listening to episode 240 of the Space Rocket History Podcast, entitled Apollo 12, the Saturn V Instrument Unit. Hope you enjoyed this episode. It was a pleasure to bring it to you. I'd like to give a big shout out to all my longtime listeners. Thanks for staying subscribed, and extend a warm welcome to my new listeners. I'm glad you're here. In case you haven't heard, the first 43 episodes of the podcast are now available on the Space Rocket History Archive. This means that the first 43 episodes are once again available on iTunes, Stitcher, Google Play, and all your favorite podcatchers. To find the archive episodes, search for Space Rocket History Archive. My server plan allows me to add 100 megabyte of episodes per month, so I plan to get some more archive episodes up in February. Today, we salute my moon emoji donors. These donors have donated for 3 years in a row and receive a moon emoji next to their name on the donors page. Thanks, moon emoji donors, for your continued support. I had several afterthoughts about this week's episode. First of all, I want to sincerely apologize for the poor quality of some of those audio clips. I tried to clean them up as best as I could, but I just could not get all that background noise out of it. I almost decided to leave them out, but they seemed to add more than they detracted from the episode, so I put them in. What made these poor quality episodes so special is they were made by Brooks Moore, who was the director of Marshall Space Flight Center's Astrionics lab during the Apollo era. I actually got to meet the 91-year-old Brooks Moore during my visit to the Space and Rocket Center in Huntsville. He was volunteering as a docent. It was an honor to meet someone who knew so much about the instrument ring and was willing to talk with me for a few moments. Now, just as importantly, I want to thank one of my podcast supporters, and that is Jonathan Pointer, for all his contributions to this episode. I cannot overstate how important Jonathan was to this episode. If it were not for him, we probably would not even have had this episode. So I want to thank Jonathan sincerely for helping me out on this episode and providing all the research data. I sincerely appreciate it. Last week, during my visit at the Space and Rocket Center in Huntsville, I got to get up close and personal with the instrument unit. They have an exhibit of it in the Davidson Center, and it was an impressive piece of hardware, and I looked it over pretty good. I spent some time there. Keep in mind, this IU controlled where the Saturn had to go, and it made its own decisions with regard to its operation as it flew. Not once did it fail its human cargo, and in the case of Apollo 12, it saved the mission. I also want to emphasize the importance of the launch vehicle digital computer. Much attention has gone to the computer aboard the Apollo command module, and the launch vehicle digital computer has sometimes been overlooked. That computer was on the leading edge of technology. The launch vehicle digital computer was historically significant. It used the early high-density printed circuit boards with integrated circuit chips. It's been called the mother of motherboards. They were a giant step ahead from the Mercury and the Gemini electronics. Okay, last thing I want to tell you. In case I wasn't clear on the voting thing, I want to explain it a little bit more. Because of the critical task the launch vehicle digital computer performed, reliability was very important. Triple redundant logic was used to achieve this. The computer contained 3 identical logic systems. So when the computer was making a decision, each decision was voted on by all 3 logic systems. This meant that even if one of the logic systems disagreed with the other 2, the decision would be made by the 2 logic systems that agreed, and it was assumed the 3rd logic system was in error. This voting system produced a result that was highly reliable. Okay, I have posted some pictures and the audio for this week's episode on my homepage, spacerockethistory.com. Hope you check that out. I was very pleased to receive several new donations to support the podcast over the past 2 weeks. Martin K. from Germany donated at the Soyuz level and earned his moon emoji. Michael S. from the UK donated at the Apollo level and earned his rocket emoji. David H. from Indiana donated at the Apollo level. Graham S. from the UK donated at the Soyuz level and earned his moon emoji. Adrian R. donated at the Orion level and earned his rocket emoji. Rich M. from Virginia donated at the Apollo level and earned his shooting star emoji. Robert M. donated at the Mercury level and earned his satellite emoji. Tom B. from Vancouver donated at the Vostok level. Jonathan M. donated at the Vostok level. Randy R. pledged on Patreon at the Apollo level. Eric P. pledged on Patreon at the Apollo level and earned his moon emoji. Ronald B. increased his pledge on Patreon to the Apollo level with rocket, moon, satellite, and shooting star emojis. Ryan L. increased his pledge on Patreon to the Apollo level with rocket emoji. Simon R. pledged on Patreon at the Mercury level. So our Patreon totals have now reached 157, with a goal of reaching 218 for 2018. And our overall donors for 2018 have reached 173, with a goal of reaching 418. For those of you who are enjoying the content provided here and have not donated yet in 2018, please consider supporting the podcast if you're financially able. Keep in mind, the Space Rocket History Podcast is entirely listener funded. I depend upon your financial support to keep the podcast going. There are 3 easy ways to make a donation. You can go to the homepage and click on the orange donate button to make a one-time donation, or if you prefer, you can become my patron at Patreon by clicking on the Patreon link below the orange donate button, or you can mail me a check. To do that, just send me an email, mike@spacerockethistory.com, and I will give you my address. For those of you who have already donated for 2018, I certainly appreciate it, and I have the best item yet to be given away for this week. William Andrews, a great supporter of the podcast, sent me 2 Saturn V second stage tie tacks. It's a little pin that you put in your necktie to hold the front and back of it together. It's a tie tack is what it's called. Now these are authentic and unique and a piece of Apollo Saturn V history. I'm going to give away one this week and one next week. To select this week's winner, we gave every 2018 donor a number. I put the range in Google's random number generator and got the number for Steve Neal. That's Steve Neal. Steve, if you will email me, mike@spacerockethistory.com, and tell me your address, I will mail this out to you. This is the end of content for this week's episode, and you are welcome to stay and listen to my off-topic thoughts if you want. Thanks for sticking around, folks. I hope you enjoyed that episode. Next week, we will move on to the launch of Apollo 12. As you may remember, we have been traveling this past couple of weeks, and I wanted to update you on what has happened. We had a great visit at the U.S. Space and Rocket Center at Huntsville, Alabama, last week. It took me 2 days to see it all, but you know how I am. I like to see everything. Now, this place is really easy to locate because they have a full-scale mock-up of the Saturn V mounted vertically. And they also have a Saturn I mounted vertically, so you can get an idea of the size difference. Here's some other things they have. The Saturn V mounted horizontally, very similar to the building that they have at Kennedy Space Center, and similar to the one in Houston as well. And they have a non-flight test article of the space shuttle called Pathfinder. They've got a simulated lunar crater with a lunar module mock-up on it. They've got a Skylab training module and the largest surviving fragment of Skylab. They have a V2 rocket, and they have Alan Bean's favorite moon rock. How do I know it's his favorite moon rock? Because that's what he wrote on the display stand, that it was his favorite moon rock. They have the Apollo 16 command module. They have an A-12 ox cart, Blackbird plane sitting out front. They also have quite a few ride-type attractions. They got one called the Space Shot, and I didn't ride these because they weren't actually operating because it was so cold, I guess. But the Space Shot allows you to experience 3 Gs and microgravity. They also had a 3G centrifugal ride. And inside they had a Mars climbing wall. They had a hypership motion-based simulator. They had an International Space Station interactive walkthrough. That was inside too, and that was pretty interesting because you can walk through the part of the space station. It's a mock-up, but it looks real. And they have the Marshall Space Flight Center bus tour, which took us around to several interesting places, and I would highly recommend that one. On some days, they have docents there, and one of the 2 days I was there, they did have docents, and I got to talk to 2 of them. As I mentioned before, one of them was Brooks Moore, and he was the expert on the instrument ring, and the other docent was Jim Jenkins, and he was an expert on the first stage, and both of them actually worked on the Saturn hardware. So that was very interesting talking to them, and I had a great time visiting the U.S. Space and Rocket Center in Huntsville. Okay, that's going to wrap it up for this week. Hope to have episode 241 posted by next Thursday. So long for now.